Welcome to Module 15, Actuators, Valves and Dampers. In this module, we move from measurement to final control. A controller output is only a request. The real question is whether that request produced the required mechanical movement and the correct physical result. A valve command is not flow. A damper position is not ventilation. An actuator moving does not guarantee the stem, shaft or blades moved correctly. In this lesson, we will build the field habit of verifying the entire action chain: command, actuator motion, linkage, valve or damper position, flow or airflow, and process response. By the end of this module, learners should be able to explain common actuator types and control signals, distinguish command from actual position and process response, evaluate fail-safe direction and torque or force requirements, and recognize valve, damper, linkage, stroke, leakage, deadband, and hysteresis problems. The goal is practical. When the BAS says a device is open, the learner should know how to prove what actually happened in the mechanical system. This module follows the action chain. First, we trace a command from the controller to the actuator. Then we look at control types: fail position, torque, stroke time, valves, dampers, feedback, sequencing, commissioning, and field verification. Keep the main question in mind. Did the BAS request produce the correct mechanical movement and the intended process response? A final control element is a chain, not a single point. The controller sends an output. The actuator converts that signal into motion. The linkage, stem, or shaft transfers the motion. The valve or damper changes position. Flow or airflow changes. Finally, the process responds through temperature, pressure, humidity, or equipment operation. Each stage can fail independently. This is why command, feedback, and physical outcome must be separated during troubleshooting and commissioning. Actuators can be two-position, floating, analog voltage, analog current, pneumatic, or network controlled. Each type has a different troubleshooting method. A floating actuator depends on timing and may lose position after manual operation or power interruption unless it is resynchronized. An analog actuator depends on correct signal range, scaling, direction, and power. A networked actuator may have priorities and modes that are invisible if the operator only looks at one graphic. The control type tells us how the request is communicated. It does not prove movement or outcome. Fail position should be selected by risk analysis. A preheat coil valve in a freezing climate may need to fail open, but that decision also depends on pump availability, damper position, air temperature, low limit protection, and operator response. A smoke or isolation damper may need a different fail action. Non-spring actuators may hold position or use capacitor return. Do not assume fail-safe action from the symbol on the drawing. Test it and document the result. An actuator is not only a signal device. It must produce enough torque or force to move the connected valve, damper, spring, seal, or linkage under actual differential conditions. Stroke time also matters. A valve that takes 90 seconds to move cannot correct a process in 5 seconds, no matter how aggressive the control loop is. In the worked example, a 9-second pulse on a 90-second floating actuator suggests 10% ideal movement. But actual position may differ because of load, travel limits, loss of synchronization, or mechanical slip. A valve may be commanded closed and still pass flow. A valve may be commanded 50% and deliver far more or far less than 50% of design flow. Valve authority, close-off pressure, flow direction, leakage, seat condition, debris, actuator setup, and differential pressure all affect the result. If a coil heats or cools when the valve is supposed to be closed, verify the condition with pipe temperature, flow evidence, differential pressure, and physical inspection before blaming the sequence. Dampers are not perfect gates. They leak. Their performance depends on construction, seals, size, pressure, installation, linkage, and blade arrangement. Opposed blade and parallel blade dampers can create very different airflow and mixing characteristics. BAS graphic may show the actuator position, but it may not prove blade position. In mixed air systems, even correct damper motion may create stratified air that misleads the sensor. Field verification is essential. This is the core engineering idea of the module. Command, position feedback, and process response can all be different. The controller may request 60%. The actuator may move to a different physical position because of deadband, hysteresis, or calibration. The process response may be even more nonlinear because valves and dampers do not convert position into flow perfectly. The professional does not stop at the command. The professional verifies the resulting physical response. Sequencing requires more than ordering outputs on a screen. Heating and cooling valves need deadband or another coordinated strategy. Outdoor, return and relief dampers must work together. Economizer and mechanical cooling must transition without creating comfort, humidity, or pressure problems. Face and bypass dampers require proof of the delivered outlet condition. Multiple valves need clear load-based logic. The question is always, when one device moves, what else should change to prove the sequence is doing the intended work? A commissioning test should be safe, documented, and useful. First, confirm authority and safety boundaries. Record the as-found condition before resets or adjustments. Then stroke the actuator in a way that does not create unacceptable operational risk. Verify full travel, timing, direction, endpoints, binding, and linkage. Most importantly, measure the process outcome. Did flow, airflow, pressure, temperature, end switch status, or equipment response change as expected? Finish with an as-left record that another professional can understand. Here's a practical field case. A cooling valve showed 100% open, but the coil leaving air temperature stayed high. If the team trusted only the BAS graphic, they might have changed the sequence or blamed chilled water temperature. Field inspection showed the actuator moved, but the stem coupling had slipped. The valve remained nearly closed. The lesson is that actuator motion is not the same as valve stem motion, and valve position is not the same as delivered cooling. Verify the boundary where the result first stops matching the expectation. Most mistakes in final control troubleshooting come from stopping too early. A command is treated as proof, a moving actuator is treated as proof, a closed command is treated as zero flow. A symptom disappears and the work is closed without testing recurrence. The field checklist protects the team. Document the function and mode. Confirm safety and authority. Verify command, power and output. Observe mechanical linkage and stroke. Measure the process response. Retain as found and as left evidence. The correct answer is C. A valve position report does not prove flow or delivered capacity. The professional response is to verify possible boundaries: isolation valves, air-bound coil, pump status, stem or linkage movement, feedback scaling, and actual water temperature difference. Raising pressure or replacing the valve without evidence can waste time and may hide the real fault. For the assignment, select one actuator, valve or damper and map the entire action chain. Record command, power, actuator movement, linkage, position, process response, fail action, and evidence. If it is a real site, follow site authorization and safety procedures. If it is a practice case, design the test and explain what evidence would prove the result. The module takeaway is simple. A controller output is only a request. A professional verifies mechanical movement, process response, fail behavior, and residual risk before closing the issue. Next, the course moves into indoor air quality and ventilation.